Also, you'll see a name, Cynthia, on here. She's not able to attend today, but some of these slides are hers. So I just wanted to acknowledge that. So we have the task of talking about resilience, and I'm again going to be the academic, the professional nerd. Not quite as exciting as the sham wow guy. I tried. So I've got this first little bit, concepts and definitions, and then Karla's going to take you through some examples from Manitoba that they've been working on. Cynthia and Karla separately have been working on a couple of projects that hopefully demonstrate some of the concepts that I'm about to present. So I showed this to you yesterday, this adaptive cycle from resilience theory. Right? So there's that word resilience. This adaptive cycle that I've shown you is sort of two-dimensional, but there's a third dimension to it, and that third dimension is resilience. Right? So what we have here is a complex system that flips back and forth between two sorts of kinds of domains, right? You have something that grows into a climax community, and that's that succession kind of example we talked about yesterday, and then it's destroyed, through fire or something like that, and then rebuilds itself. And so it sort of goes back and forth. And you can see these kinds of systems not just in forest patches and fires, but in lots of kinds of things, including human systems and coupled human and natural systems. So the third dimension is resilience. And to get to that, I want to sort of back up a little bit and talk about this idea of linear relationships, because it has some bearing on this idea of resilience. So just very quickly, normally when we think of something that's linear, we think that there's some kind of relationship that is expressed by an increase in one unit is an increment in the other unit, and it just sort of goes one to the other. One thing leads to the next thing, and it's represented by this sort of line. Here's that example of the size of a fire and foliage density that I mentioned yesterday. Usually when we say linear, we mean a straight line, and when we say nonlinear, we usually mean a line that's curved, like an exponential kind of thing. And it's nonlinear in this sense because an increment of one unit leads to an increment of more or less than one unit on the other axis. Now, this is the way we normally think about it, but what this is from the perspective of complexity is not just linear, but causally linear. So that this line is connected the whole way. So one increment here leads to a predictable increment on the other axis, this two-dimensional kind of representation. But what we're dealing with is complex systems in which we don't always have this causal linear kind of setup. There's a discontinuity often in the way that these systems move, right? And in lay terms, we recognize this with the term tipping point. It'll reach a certain point, and all of a sudden it'll fall off of that line and go somewhere else. Not in a causally linear kind of way. It's not that one thing leads to the other thing. It's the system all of a sudden reorganizes, right? And that is something that doesn't fit on that line. So what we have actually is multiple possible lines that the system can flip. Now, I don't want to really like to, but I'm not going to start talking about catastrophe theory and chaos theory, which is where this stuff comes from. That's a little representation of a simple catastrophe landscape. Catastrophe meaning sudden change in the French way, not the English way, which means disaster. Change can be good or bad, or neither. But I put this up here because now we've got, I can use this to show you two lines that a system might organize around. And I'll use this to demonstrate that resilience. This is the sort of edge of this three-dimensional one. It's just a simplification for the purposes of talking about it. And these edges, or the unknowns, will be the sort of planes that's, flat parts on that landscape, are what are known as attractors, equilibrium attractors. You don't really have to worry about the jargon. But this is a stable area, the meaning that this behavior of the system can move along this line until it reaches a tipping point, in which case it falls off that line and either goes back to it or it falls far enough away that it's snapped over to another equilibrium attractor. Now this is, I know, all academic, but it helps to understand where we're coming at when we actually say resilience. So the idea here is that the system can be pushed off of that line. There's some shock to the system. You know, there might be a fire, and that's shocking the system and it moves off. Or it might be, you know, spruce bug burn or pine weed. Or, maybe it's you know, a revolt in a political system or something like that. Resilience is an expression of how far you can push the system away from that attractor, and it reorganizes. It comes back and stays the same. Right? It moves within that domain of behavior. Past a certain point, if you push it too far away, see it comes back, in this case, that's resilience. If you push it too far away and it moves beyond the point in which it can regain its organization around that attractor, it will find another, it will either disintegrate or it will find another organized sort of domain of behavior. So it'll go near or around another attractor. Right? And so it'll reorganize into a different space. And it will actually organize in a resilient way around that attractor. It'll be just as hard often to push it off of that attractor as it was to push it off the other one. So for example, this might be an example of a forest fire. What's my next slide? This might be an example of a forest fire. You know, here's the non-fire state, and here's the fire state. Right? So if you have a fire and you know, you have a non-fire kind of place, and a little fire starts here, and in this conceptual space, it's not going to start to blow up because you're not in the sort of domain area where it can find this fire attractor. It will self-extinguish. But if there's enough fuel, this is the oil density, you could have a high enough, hot enough fire if you're to, you know, to have an extra little push, like a strong wind or something like that, to push it off of that attractor, and it can self-ignite to a larger state, and then it'll start burning until, you know, it burns off the fuel density, self-extinguishes, and it falls back on this kind of thing. So there's a cycle that you can see in forest patches that might happen. Fuel density builds up, gets a spark, catches fire, burns down, self-extinguishes, just keeps going around and around and around. So you can see these kinds of cycles in lots of different. The fire one's an easy one to conceive of. So that figure 8 that we saw yesterday has a third dimension, and as that cycle goes in these systems, resilience actually changes. It becomes easier to knock it off its trajectory in some places, and more difficult in other places. And it's a little bit sort of difficult to see, but the rotation goes around this way. And so you can see that as the climax community builds up, as the system starts to consolidate its resources and becomes a little bit, I guess, more brittle, resilience actually is reduced. The system is less resilient. It's easier to destroy that system, to knock it off of that attractor. Right? And as the system disintegrates and reorganizes, it starts to grow again. And resilience is actually stronger. It's more resilient. Not right at the point where it's all disorganized, but as it's starting to organize again and there's lots of opportunity, lots of material to work with, there's more room for it to maintain its organization. And so this is a conceptual way of thinking about the concept of resilience. So basically the system becomes actually more vulnerable. They use the term vulnerable, I don't like that particular way of saying it, to shock, to change, as it becomes more structured. That's the basic kind of idea there. Now this is related to things like I mentioned, chaos theory, catastrophe theory, stuff like that. You don't have to worry about those things. But the idea of attractors is something that is important, and attractors like a domain of behavior. You can think of it, a really good metaphor, I know the lines and stuff don't quite drive home the point, but there's a metaphor of a ball and a cup. Right? And you have a cup with a little ball bearing in the bottom, and you can think of that whole inside part of the surface of the cup as the domain of behavior, and the ball bearing rolling around inside it as you move the cup as the system and its trajectory. Right? And the variables describing the system change depending on where it's rolling around in the cup, but it's always attracted to the bottom of that cup, right? And that's sort of a domain of behavior. And the resilience of the system can be described by the height of the sides of that cup. The higher the sides, the harder it is to knock that ball bearing out of the cup, right? And you're moving it. Those are the external pressures, the external shocks on the system. So it's going to move around, but it stays within the cup unless you tip it with a really hard shove. And you can picture a whole landscape full of cups. If you shove it out of one, it'll find another one. And that'll be a different domain of behavior. And the thing to know about this kind of thing is that those domains of behavior are resilient. You knock it off one, you can't just say, oh, okay, I'm going to dial it back again and we'll go back. No, you've got a whole different situation now. So when you're managing your systems, you have to think that this thing is resilient. You start to have to think, where are the tipping points? And how do I know where they are? And what's going to happen if they pass that tipping point? So that's the basic conceptual message about resilience. So I'm going to pass it over to Karla. Hope I didn't take too much time.
You can try this. Is this on?
No.
Ah, Power. There. Hi, I'm Karla Zubrycki. I'm with the International Institute for Sustainable Development, which is headquartered in Winnipeg. And I'm going to be giving, start with a more concrete example from the Manitoba watershed called South Tobacco Creek, and then I'll be linking it back to Holling's Figure 8. So it's a mix of concrete and more theoretical. Good, that works. I'm going to start with some headlines from the Winnipeg Free Press in 2004. Following the record drought in 2001 to 2002, 2004 was one of the coldest and wettest summers in decades. Farmers experienced a cool and wet growing season, early frost, and a cold and wet fall that resulted in record crop insurance payouts. It was a hard year, but the generally impressive optimism that many farmers seem to have, they looked to 2005 with the belief that it couldn't possibly be as bad as 2004. And they were right. 2005 was much, much worse. In 2005, they were hit with an onslaught of successive shocks. Again, it was more miserable and wet weather, plunging grain prices, skyrocketing energy costs, and it all led to 2005 being one of the worst farming seasons in decades. Some crops couldn't be seeded because the fields were too wet in the spring to seed at all. Some farmers that did manage to get crops into the ground had their later destroyed by floodwaters, and those crops that survived the early and later floods then found them being burned up by a drought later in the summer. But there was a relative island of resilience in the Manitoba farming landscape. The Winnipeg Free Press took note of it, publishing several articles on the small area that was somehow weathering things so much better. There was less flooded land, less damaged infrastructure, and more cropping success, as you can see from the quotes there.